Good day, everyone. So we will now continue with our next part of our chapter 4, KJM 442, Heat and Fluid. Uh, in our part 1, we have covered the topic on refrigeration. So in part 2A, we will cover the part on air conditioning. So for air conditioning, I've divided it into two parts. So in this presentation, I will cover part 2A, focusing on air conditioning based on the Dalton's law equation. In part 2B for air conditioning, we will concentrate on psychrometric chart. So as you can see here, for chapter 4, we have a total of 5 subtopics that need to be covered. So for today's presentation, we will be focusing mainly on this topic, which is the property of commercial refrigerants based on Dalton's law and Gibbs-Dalton's law of mixtures. Right. So in this chapter, uh, most of the uh, section will be covering the use of psychrometric chart as a tool to determine the properties of atmospheric air. But here, before we go to the psychrometric chart, we will determine the properties of atmospheric air based on Dalton's law and Gibbs-Dalton law of mixtures first. In our next part, which is part 2B, we will then use psychrometric chart to determine the properties of atmospheric air, and we will also be analyzing the various air conditioning processes using principles of conservation of mass and energy. So these are the objectives that we're going to cover in this presentation and part 2A. So let's begin with our introduction. So what is air conditioning? So air conditioning is nothing but it's a process of treating air to control simultaneously. So here we have the word simultaneously. So what you're doing is you are treating air around you, right? So air conditioning is nothing but a process of treating air. Why do you treat the air? Because you want to control simultaneously. The first thing, it's its temperature. So if you feel hot at home, you will switch on your air conditioner because you want to bring down the temperature in the confined space where you are staying in. So that is controlling the temperature. So the next thing that you want to control is the humidity. So we will cover in this part of this chapter what is the definition of humidity, and you will see that in Malaysia our humidity is quite high. It can be as high as 80 to 90%. So we need to control that so that you can achieve the human comfort level that you want from the air conditioning processes. So those are the two controls that you want to have when you want to switch on your air conditioner. The next is cleanliness. So air around us might be dirty, so you need to filter out the air. So there's a lot of dust in the air. So the air conditioning, one of the objective of having an air conditioning is to also clean the air around us so that you can maintain the cleanliness in a confined space where air conditioning is running. And thirdly is the distribution. So if you have a central air conditioning system, you will need to distribute this cool or hot air around the entire distribution system, and this air conditioning system allows you to do that. So as you can see here, so we have a process. So air conditioning is nothing but a process of treating air to control simultaneously these four parameters. The temperature, now the temperature here is either you can reduce the temperature or you can increase the temperature. So in Malaysia, definitely, because our mean temperature is around 35 degrees Celsius. So we will then use the air conditioning to lower down the temperature to almost 24 degrees Celsius. So that's the human comfort temperature. Humidity in Malaysia is high too, so we can use the air conditioning system to reduce the humidity to the comfort that we are comfortable with. And there are a lot of dust that we have in the air around us. So you can use the air conditioning system to clean the air. so that you can trap the dust in the air conditioning system, and the air that is delivered to you after the air conditioning process is clean. And you also need to distribute air. As you can see in the classrooms, we have a lot of air conditioning ducts that distributes cool and treated air to all the rooms. So this is some introduction. So air conditioning, as we have discussed, is purpose to maintain a confined space at the desired conditions. And how do you do that? Is by either heating, or you can cool down the air, or you can humidify if the humidity level is too low, or you can dehumidify if the humidity is too high. So these are the four processes that you can have in order to maintain a confined space at the desired conditions. Now so human body comfort depends on these three factors. So the factors are temperature, humidity, and air motion. So we want to live in an environment that is neither hot nor cold, neither humid or dry. However, comfort does not come easily, since the desire of the human body and the weather usually are not compatible. Right? So just like in Malaysia, the temperature of the surrounding can be in this range, 27 to 42 degrees Celsius according to monsoon season. And the comfortable temperature that suits our human body comfort is between the range of 20 to 24. So achieving comfort requires a constant struggle against the factors that cause discomfort, such as high or low temperatures and high or low humidity. So if you look at our human body can be viewed as a heat engine whose energy input is food. As with any other heat engine, the human body generates waste heat that must be rejected to the environment if the body is to continue operating. Now, if you look at the rate of heat generation, it depends on the level of activity that we are in. So if you are an average adult male and if you are sleeping, you will be generating about 87 watts of energy. And this is heat energy that is released into the surrounding. If you are resting or doing your homework, you will be releasing about 115 watts. And if you are doing heavy physical work, then you will be releasing almost 500 watts of energy. So our deep body temperature, if you are a healthy person, is always held constant to about 37 degrees Celsius. Now, your body will feel comfortable if you are in an environment in which you can dissipate this waste heat comfortably. Now, we know heat transfer is proportional to the temperature difference. Therefore, if you are in a cold environment, for an example, if you go to Cameron Highlands, our body loses more heat than it normally generates, which results in feeling of discomfort. Now the body will try to minimize this energy loss by cutting down the blood circulation near the skin, and this will cause a lot of discomfort to you. So in order to avoid that, what we will do is we will add on more clothes so that we will become much more comfortable, and this will introduce a thick layer between our body and the environment, and this becomes an insulation layer so that you can remain comfortable in a cold climate. Now if you have a hot environment like what we have in Malaysia, we are in a situation where we do not seem to be dissipating enough heat from our bodies, and we feel as if we are going to burst. So what we do is we dress very lightly so that it is easier for heat to get away from our bodies, and we reduce the level of activity to minimize the rate of waste heat generation in the body. Now the simplest way to do that is we can also turn on the fan to continuously replace the warmer air layer that forms around our bodies, as a result of body heat by the cooler air in other parts of the room. Right? So this is, we also sweat. So in a hot environment, as you can experience in Malaysia, we also perspire, and then by sweating more, as this sweat evaporates, it absorbs our heat. So this heat is in the form of latent heat from the body, and once this sweat evaporates, it cools our body down. Now if you sweat a lot, and prolonged sweating without any fluid intake will cause dehydration, right? And this will also reduce sweating, which may lead to a rise in body temperature and cause you a heat stroke. So as you can see from the slide here, the comfort of the human body depends primarily on these three factors. So the temperature that we are comfortable in should be maintained between 20 to 24 degrees Celsius. And you can use air conditioning easily to maintain this. In a hot climate country like Malaysia, we use air conditioning to absorb the heat out of the confined space and reject it outside into the surrounding. But let's say if you are in a cold climate country during winter, obviously the temperature outside is going to be lower than this temperature range. Then what you do is, instead of absorbing heat from the confined space, then you will be adding heat into the confined space so that you can raise the temperature of the room to this comfortable temperature range. Another factor that affects your human body comfort is the humidity. So humidity must be maintained between 40 to 60%. So humidity is nothing but the amount of moisture present in air. So the higher the moisture, the higher the humidity. So Malaysia, our humidity is between 70 to 85%. So we can actually use air conditioning to reduce the humidity so that we can achieve the comfortable level, which is between 40 to 60%. Now air motion also plays an important role in human comfort. It removes the warm, moist air that builds up around the body and replaces it with fresh air. So therefore, air motion improves heat rejection by both convection and evaporation. Now, air motion should be strong enough to remove heat and moisture from the vicinity of the body, but gentle enough to be unnoticed. So you don't want a high velocity air blowing over your body because that becomes uncomfortable. So your air ventilation and the velocity of air motion is very important. So these are the three factors that are important in order to achieve the human body comfort. Now there are other factors that affects this comfort. The first is the air cleanliness. Now if you remember, we need to clean our air from the dust, and 80 to 90% of the dust constitutes of human body dead skin. So we need to clean this air so the air can be filtered through the air conditioning, and then the air that is then delivered to you will be cleaner than the air that was in the confined space. And we also need to make sure that the air that is being conditioned through the air conditioning process is free from any odor or any smell. In certain cases, you can also control the radiation and other factors that we will discuss later in the presentation. So these are the human body comfort, and then it depends on these three factors. And remember, in the subsequent presentation, we will be learning on how to control these two parameters, especially the temperature and humidity, so that you can achieve the human body comfort between 20 to 24 degrees Celsius and the humidity level between 40 to 60. Now if you look at this diagram, it shows that we use conditioned air in our daily life. If you have a medium-sized hospital, the energy usage is shown here in a pie chart, and you will see that the air conditioning constitutes almost about 40% of the energy used. In a large hotel, air conditioning can constitute almost about 54% of the total energy used for that premise. In a large office building, we will see that 50% of the energy bill comes from air conditioning alone. So like it or not, air conditioning plays a very important role in our daily life. Whether you go to a hospital, whether you are in a hotel, whether you are in an office building, and even if you are in an institution like UITM, you need air conditioning badly. So we depend a lot on air conditioning to achieve our human comfort. So next, pay attention that we badly need conditioned air for other purposes too, not just for us to reach the human comfort level. We also need air conditioning to maintain a uniform temperature during manufacturing processes. This is because any fluctuating air temperature will result in poor product quality. So if you have non-uniform temperature during manufacturing processes, it can cause shrinkage, and this will result in poor product quality. And you also need dry air in textile industry and library. Now consider library. In a library, we have a lot of books. And if you have moist air in the library, this will result in fungus formation in textile or books. So in order to avoid this, we can treat the air in the textile industry and also the library so that we can only deliver dry air without any moisture, so that you don't have this issue of fungus formation. Next, we also need conditioned air in hospital or operation theater or in a clean room. So clean room is where you manufacture your integrated circuits, the wafers, all right? So you need uh, very clean air in a clean room where you manufacture wafers. It has to be dust free. Even a single speck of dust which falls onto a wafer can destroy the entire wafer. So in our hospital, we need to make sure that the bacteria and dust are filtered and removed from the air. Because if you have a lot of bacteria floating around in the hospital, this can cause infection and patients might die because of septic shock caused by the bacteria. And finally, we also need cool air in computer and server rooms. So server rooms tend to become hot because they process data in a very big scale, and this releases a lot of heat. So in order to maintain the temperature in the computer and server room, we need to supply cool air. So this will help in cooling of electronic equipment, and if you do that, this becomes very essential to avoid damage, because any computer or server room exposed to high temperatures will result in electronic equipment damage. So cool air supplied to these rooms will help to avoid this. So you can see now, air conditioning is more than cool air for human comfort. We need air conditioning for many applications. Now there are various applications of air conditioning, and then if you have time, you can actually go and have a look at this ASHRAE handbook for standard design requirement. So ASHRAE is acronym for American Society of Heating, Refrigerating and Air Conditioning Engineers. This ASHRAE handbook is available online. So I've provided you with a link, so you can actually go and have a look at this handbook, and then see what are the type of air conditionings they have, what are the standards that they follow. If you intend to become a HVAC engineer once you graduate, then this is one of the most important book that you must have with you, because all your design requirements, design conditions are specified clearly in this handbook. So in this slide, we will see how an air conditioner works. So as you can see in the diagram here, you have the basic components that we have covered in our refrigeration cycle. So what you see here, you have a compressor, you have a condenser, you have an expansion valve, you have an evaporator. So basically air conditioners, they work with the principle of refrigeration cycle. So what happened is the air from the confined space is actually pulled into the duct, all right, with the help of a fan here which is located near to the evaporator. So this air needs to be conditioned. So if you are in a confined space where you need to cool down the air temperature, so this air is then channeled through the evaporator. So as the air flows through the evaporator, the heat is absorbed by the refrigerant in the evaporator. So as a result of that, the cooled air is then delivered to the confined space. So this is how you cool down the air. Now the heat absorbed by the evaporator is then sent to the condenser of the air conditioner. So with the help of another fan here, this heat is then expelled to the surrounding atmosphere. So as a result of that, the refrigerant is now cooled and then can be recycled back into the refrigeration cycle to continue absorbing heat from the confined space as explained earlier. So as you see, the refrigeration cycle is the basis of how air conditioner works. Right? So we have compressors, condenser, expansion valve, and evaporator. And this is where you get the cooled air coming in, and the condenser is the place where you reject the heat from the refrigeration cycle. Now we go to the psychrometry. Now what is the psychrometry? Psychrometry is the study of air. So what are the constituents of air? All right. So if you look at this statement, psychrometry is the science of studying the thermodynamic properties of moist air and the use of these properties to analyze conditions and processes involving moist air, that is the study of atmospheric air. Now if you look at these two words, you have moist air. So meaning to say that you have air embedded with some moisture. Right? So that is the psychrometry. Now air is a mixture of nitrogen with oxygen and some small amount of some other gases. So what are these gases? We will see in a while. So air in the atmosphere normally contains some water vapor. So we call it as moisture and refer to as the atmospheric air. So the water vapor in the air in terms of content by mass can be between 0 to 3%. So if you have 0% mass of water vapor, then the air in the atmosphere is called as dry air. All right. So if you have some moisture in it, then it becomes what you call the mixture of air and moisture. So air that contains no vapor, so no vapor means 0% water vapor, we call it as dry air. So these are the constituents of atmospheric air. So you can see here we have nitrogen, oxygen, argon, carbon dioxide, and hydrogen. Nitrogen constitutes almost about 78% by volume. Oxygen is about 21% by volume. And then the balance less about 1% constitutes of argon, carbon dioxide, and hydrogen. And this is again, all these parameters are represented in a pie chart here. You can see that the major constituent of atmospheric air is nothing but your nitrogen. Then you have about 21% of oxygen, and then about less than 1% it consists of argon, xenon, neon, hydrogen, helium, krypton, and carbon dioxide. Now for dry and water vapor of atmospheric air, the atmospheric air consists of dry air and water vapor. So this atmospheric air, you have two constituents. One is the dry air, the other one is the water vapor. Now we will now go to Dalton's law. So in Dalton's law, let's look at it. Partial pressure states that the total pressure of the gases is the sum of the partial pressures. So the partial pressures in atmospheric air constitutes of the pressure of dry air and the pressure of water vapor, right? So that is based on Dalton's law. So the total pressure constitutes of pressure of dry air plus pressure of water vapor. So that is the total pressure. For an example, if you have atmospheric pressure of 1 atm, so that 1 atm constitutes of pressure of air plus pressure of water vapor. So the other point that to be considered here is your volume, or the enthalpy of the mixture of gases is the same as the volume occupied, or the enthalpy of the constituents of each gas at its partial pressure. Right? So we will see in examples on how to use this formula. So bear in mind, based on Dalton's law, the total pressure of atmospheric air constitutes of the partial pressure of air, dry air, plus partial pressure of water vapor. Now the temperature of atmospheric air in air conditioning applications ranges from -10 degrees Celsius to about 50 degrees Celsius. So whenever you have this range, any temperature that is below 50 degrees Celsius for atmospheric air, then you can treat the air to be an ideal gas. So the moment you can treat the air as an ideal gas, you can start using the formula PV equals to nRT. And as a result of that, then you can find the enthalpy based on this formula. Cp, specific heat capacity of air, and then this is the temperature. Now bear in mind, this temperature is always in degrees Celsius. And the specific heat capacity for air, the unit is always in kilojoule per kilogram degree C. So we will see in our examples later on how to use this formula. So this is the enthalpy of air. Alright, so bear in mind the temperature is always taken in degrees Celsius, not in Kelvin. Right, so this is another note on dry and water vapor of atmospheric air. So as you can see here, partial pressure of water vapor is usually referred to as the vapor pressure, and it is the pressure water vapor would exert if it existed alone at the temperature and volume of atmospheric air. So since water vapor is an ideal gas, so the enthalpy of water vapor is a function of temperature only. So which we have seen earlier, right? So this can also be observed from the TS diagram. So we are given a TS diagram here, right? So where you can see the constant enthalpy lines. So these constant enthalpy lines coincide with constant temperature lines at temperature below 50 degrees Celsius. So at any temperature below 50 degrees Celsius, your H is considered to be constant. So therefore, the enthalpy of water vapor in air can be taken to be equal to the enthalpy of saturated vapor at the same temperature, right? So this will lead to, for these conditions, so the enthalpy of water vapor can be approximated based on this formula. So since, as what we've discussed, so saturation pressure of water vapor in air mixture is below this, or we can say that the temperature is always below 50 degrees Celsius. And if we use this formula, right, as you can see from this table, so if you find the enthalpy based on the equation given here, and you find the enthalpy based on the table given in the property table and charts, you will see that the difference is very small for temperature range between -10 to 50 degrees Celsius. So for this range, you can safely use this equation to find out the enthalpy. Again, point to note, this temperature here is always in degrees C, not in Kelvin. So we'll be using this formula again and again in calculating our enthalpies in our subsequent sections. Now let's look at what is specific and relative humidity of air. So these formulas are important. So humidity is nothing but amount of water vapor in the air. Higher humidity reduces the effectiveness of sweating. So if the humidity is high, our sweat will not be able to evaporate. So this will reduce our effectiveness of sweating, and this will in turn slow down the cooling of the body by reducing the rate of evaporation of moisture from the skin. So as mentioned earlier in our presentation, the humidity level in Malaysia is very, very high. So you become very lethargic when you start sweating because it takes a very long time for the sweats to evaporate when the humidity is very, very high. So the main measurement of humidity is given as follow. So the first parameter that we can use to measure humidity is called specific humidity, or we can also call it as absolute humidity. The symbol is given here. The symbol is called omega. So this is defined as the ratio of the amount of moisture in the air to the amount of dry air. So this is given in the formula here. All right. So omega is the amount of moisture in the air to the amount of dry air. So this is based on the definition, and then you can modify this equation to introduce your partial pressure of your water vapor, 0.622 times partial pressure of water vapor divided by this P here is the total pressure minus the partial pressure of water vapor again. So as you can see here, there are no units for omega, but we quantify it in terms of kilogram of moisture to kilogram of dry air. So specific humidity, if you want to specify it, it is always in terms of kilogram of water moisture to kilogram of dry air. So this is the unit, kilogram of H2O divided by kilogram of. Okay, now we'll go on to the relative humidity. Relative humidity is denoted by this symbol phi. So relative humidity represents the amount of moisture the air holds to the maximum amount of moisture the air can hold at the same temperature. Now the amount of moisture in the air has a definite effect on how comfortable we feel in an environment. However, the comfort level depends more on the amount of moisture the air holds relative to the maximum amount of moisture the air can hold at the same temperature. Now the ratio between these two quantities, so the ratio between these two quantities is called relative humidity. So mass of water vapor in air divided by mass of water saturated moisture in air. So that is given in based on the definition. You can also calculate it based on the pressure here. So partial pressure for the water vapor and the saturation pressure at a given temperature. So as you can see here, we have an example. So you have a dew point temperature with a vapor pressure of 1.491, and then the saturation pressure is given for the same temperature as 3.169 kilopascal. If you find the ratio of this will give you a relative humidity value of 0.47. We can then convert this into percentage, which will give you a 47% of relative humidity. So most of our values of relative humidity are given in terms of percentage, or in terms of unity, the relative humidity ranges from 0 to 1, and in terms of percentage, it goes from 0 to 100%. Now, a point to note here, both specific humidity and relative humidity can be written as shown in this formula and also in this formula. So they are interconnected. So if you want to find your specific humidity based on the relative humidity given to you, you can use this formula. And if you want to find relative humidity based on the specific humidity given, then you can use this formula. And bear in mind, Pg is nothing but your saturation pressure at the given temperature. We will see in the examples later on how to use these formulas to calculate your saturation pressure and also your vapor pressure as shown in the formulas here. You also have the mass and enthalpy of mixtures, right? From the definition of relative humidity, the mass and enthalpy mixtures, you can express them as follow. So the total mass for atmospheric air can be given as mass of the dry air plus the mass of water vapor. If you factorize it to mass of dry air, this will result into this formula, and based on the definition earlier, we know mass of water vapor divided by mass of dry air will result in your specific humidity. So total mass of the atmospheric air can be written either in this formula, or you can calculate it based on this formula, where ma is your mass of dry air. So this is the enthalpy. So the enthalpy, you can use the same relationships again, right? And then if you change your enthalpies, right, for your dry air and your moisture, so this will result in this formula. And then if you cancel out the dry air mass with this, that will result with HA. And then this MV over MA is nothing but your omega. So that will give you omega here, and this is your enthalpy of water vapor. So that will result in this formula. This is the enthalpy. So you can use the enthalpy of mixture to calculate out the enthalpy for problems related to air conditioning. And this is the associated unit. The unit is nothing but kilojoule per kilogram dry air. Okay, so this formula can also be equated to this formula. Again, bear in mind the temperatures here are in degree Celsius. So we will see how to use these formulas later in the examples in our next subsequent presentation. Now we also have another parameter that you need to understand. This is called dew point temperature. Now, if you live in a humid area or humid country like Malaysia, you are probably used to walking up most summer mornings and finding the grass wet. Why? You know it did not rain in the night before. So what happened? So now, even if it's not raining, but in the morning when you start walking over the grass is wet. So how is that possible? Now, the excess moisture in the air during the night simply condensed on the cool surfaces of the grass, forming what we call dew. Dew is also known as embun in Malay. So you will see that we have this dew formation of grass early in the morning, and this is formed because of this dew point temperature, right? So in summer, a considerable amount of water vaporizes during the day, right? Just like what happens in Malaysia. As the temperature falls during the night, so does the moisture capacity of the air. So this moisture capacity is the maximum amount of moisture the air can hold. So after a while, the moisture capacity of air equals to its moisture content. At this point, your air is saturated and its relative humidity is almost 100%. Any drop in this temperature will result in condensation of some of this moisture, and this is the beginning of dew formation that you see on the grass. So the dew point temperature, if you look at it, is defined as the temperature at which condensation begins when the air is cooled at constant pressure. All right, in other words, dew point temperature is the saturation temperature of water corresponding to the vapor pressure. So this you can see here on a TS diagram here. So on the TS diagram, as the air cools at constant pressure, so as the air cools at a constant pressure, the vapor pressure remains constant, right? So the vapor pressure remains constant. Therefore, the vapor in air state 1, right, undergoes a constant pressure cooling process until it strikes the saturated vapor line at state 2. The temperature at this point is called dew point temperature. And if the temperature drops any further, some vapor will then condense out. Right? As a result, the amount of vapor in the air decreases, which results in decrease of PV. So the air remains saturated during the condensation process and thus follows a path of 100% relative humidity. So the ordinary temperature and the dew point temperature of saturated air are identical, right? So now you may have noticed this if you look at this diagram, right? So when you buy a cold drink from any canteen on a hot and humid day, you will see that there are dews forming on the outer surface of the glass. So the formation of dew on the outer surface indicates that the temperature of the drink is below the dew point temperature of the surrounding air. Right, so this is the information of dew point temperature. So we will be using this parameter again for our calculation later on. Now we also have dry bulb and wet bulb temperature. Now if you look at the thermometers here, right, so let's read this. So we have wet bulb temperature is read from wet bulb thermometer, which is an ordinary liquid in glass thermometer whose bulb is enclosed by wick moistened with air. Now if you look at this set of thermometers, this is called sling thermometer, hygrometer. So you have two thermometers, right? So one thermometer at the bulb here is exposed to air. Another thermometer here is covered with a wet wick, right? So in other words, you can also have wet cloth. So what happened is, so this thermometer will read the reading as it is of the surrounding air. So the temperature of the surrounding air will be illustrated here. Now the temperature of this thermometer will be lower than the temperature of the dry bulb thermometer. So you call this as dry bulb thermometer because there's nothing covering it, is dry. This is called wet bulb thermometer because the bulb here is covered with a wet wick. So you call this a wet bulb thermometer. Now the temperature here is the temperature of the surrounding. Now what do you think is the temperature for the wet bulb thermometer? The wet bulb thermometer will show a lower temperature compared to the dry bulb thermometer. The reason for this is when you cover the bulb with a wet cloth or a wet wick, some of the heat is lost to the surrounding by means of evaporation. So remember, this wick is wet and surrounding you have air. So part of the moisture from this wet wick will tend to evaporate into the air surrounding it. So when the water vapor evaporates, the temperature surrounding the bulb will drop, and it depends on how much evaporation is taking place. If the humidity of the surrounding air is low, then you will have very high evaporation. If the humidity of the surrounding air is high, the evaporation is lower, and as a result of that, the temperature drop will be lower. So by comparing these two temperatures on the thermometer, then you can actually measure the humidity level. So that is the basic science behind it, on how to measure the humidity level. So this is a sling hygrometer, but in today's world, right? So what we have is advances in electronics has made it possible to measure humidity directly in a fast and reliable way. So you don't see this much. You see a lot of these electronic devices. So it appears that a sling psychrometer and wet wick thermometer are about to become things of the past. So this is becoming things of the past. Today you have handheld electronic humidity measurement devices. So you have this handheld, or you can also put it over the wall. And the measurement here is actually based on the capacitance change in a thin polymer film as it absorbs water vapor. And the device is capable of sensing and digitally displaying the relative humidity within 1% of accuracy. So that is the modern device that we have nowadays. So this was the earlier devices that is becoming almost extinct. So you can find this in a lot of museums nowadays. So we are using a lot of these digital devices to measure the humidity level. Now let's look at some sample problems first before we move into our next section. So here we have a 5 meter by 5 meter by 3 meter room, which contains the air water vapor mixture at 25 degrees Celsius and 100 kPa. Now when you read this 100 kPa is the total pressure, all right, and the relative humidity phi is given at 75%. You are asked to determine the partial pressure of dry air, the specific humidity, the enthalpy per unit mass, the masses of dry air and water vapor in the room, and the dew point temperature. So how are we going to do that? So we have done all the formulas earlier. So now we will see how to use those formulas in order to get all the values from A to E. Now I've prepared a skeleton for your solution here. We will discuss the skeleton of the solution, but I want you to do all the whole problem again on your own based on the explanation given. So let's look at the solution here. So this is the skeleton that I've provided you. So look at the assumptions. So the assumption is the dry air and the water vapor in the room are considered as ideal gases. This is very important. Now we need to find the properties. So we need to look at the CP. So how do we get the value of CP here? So we will need to go to table A2 for your property table and charts. All right. So this can be found at page 909 for the property table and charts that I've shared with you. So you can go to the row that shows you air, and you can easily find what is the value of CP here, which is shown as 1.005. So that is obtained from table A to A. Now the temperature given to you is 25 degrees Celsius. So we need to find what is the saturation pressure for the moisture in the air at 25 degrees Celsius. By the way, please correct this. This is not T saturation. This is supposed to be P saturation. So this one is supposed to be P saturation, not T saturation. So you correct this. So this is P saturation, not T saturation. So P saturation here at 25 degrees C, you will need to go to table A4, which shows you the saturated water temperature table. So you go to the temperature which gives you 25 degrees C, and then you will see that your saturation pressure is 3.1698 kilopascal. And from the same table, you can also find the enthalpy for saturated vapor. So at 25 degrees C, the enthalpy for saturated vapor is 2546.5. Now these are the values for the water vapor. P saturation for water vapor, and this is the enthalpy for water vapor, all right, in the air. So then we go to the first part of the solution. So as you can see here, we have done our Dalton law. So for Dalton law, we have total pressure. Total pressure is given as partial pressure of air, dry air, plus partial pressure of water vapor. Right. So this is the formula given to you based on Dalton's law. So if you rearrange, you will see that the partial pressure of air, dry air, is this partial pressure of dry air is equals to your total pressure minus the partial pressure of water vapor. All right. So you can also, because this is the first formula that you can obtain from Dalton's law, you can also find your partial pressure of water vapor based on the definition of uh, humidity ratio or relative humidity. So that is PV over PG. So we know our PG is the P saturation at 25 degrees C. So this value is given to you. So multiply with that, that will give you the partial pressure of water vapor here. We know what is the total pressure. You minus these two, that will give you your partial pressure of your dry air. So please do this. So skeleton is there. You should be able to obtain the values. Now we go to the specific humidity of air. So we will use this equation. So we have all the parameters needed. We have the partial pressure of water vapor, which we have obtained from here. And we can use the total pressure, which is given in the question. and partial pressure of water vapor, again the same value, multiply it, use this formula, and that will give you the value of specific humidity. And remember, the unit here is kilogram of H2O divided by kilogram of dry air. Now the enthalpy, again based on this formula, right? So we will use this part. So we have Cp. Cp is given here 1.005. And what about T? Temperature is in 25 degrees C. So use 25 degrees C. Omega is obtained from here, and Hg is again given here, which we have found from table A4 earlier. So substitute it, then that will give you the value of H. Right? So the enthalpy of water vapor could also be determined from the earlier equation. If you want, you can find it from the equation that we've discussed earlier, and you will see that this is very much identical with the table A4 that we have here. So give it a try, use the formula that we've discussed earlier, see that you are able to get this value from the formula, right? And you will see that they are almost identical. Now to find the mass of dry air and mass of water vapor, we will first need to find out the volume. So the volume of the room, as you can see, the length, width, and the height of the room is given. So you can find the volume of the room, right? And then if you still remember the formula, P V, right, equals to M R T, right? So from here you can rearrange this formula so that you can find what is the mass. So we are going to find the mass of dry air and mass of water vapor. So for mass of dry air, we have the partial pressure of, which is given here, partial pressure of dry air. Volume is same as this because all three occupies the same volume. So we will use the same answer that you've obtained from here, and the value for R can be obtained from the table and charts. All right. So you can find the gas constant. So this is given here. All right. So you can use that, and the temperature. So substitute it, and you should be able to get the value that you are looking for. And my question to you now is, what will be the unit for temperature here? So are you going to use Kelvin, or are you going to use degree C here? So the unit here, so unit for this should be in Kelvin, not in degree C. So please note here, for this formula, the unit for temperature must be in Kelvin, not in degree C. So you've got to convert this 25 degrees C into Kelvin in order to substitute here. Now repeat the same thing for the mass of water vapor. So you know PV, so PV is given here. So this is our PV. So use that value. V volume is the same, R is again the same value that you have, and then T is the same, and you should be able to get what you call that, the mass of water vapor. Now you have to be very careful. The R value here for water vapor is different than the R value that you have here for air. So for air you can use 0.287, which is given here. Now it's your job to find out what is the R value for the gas constant value for the water vapor. All right. So just to let you know, the R value for water vapor is 0.4615. So learn and go and find out where to find this value from the property table and charts. All right. So then once you've got that, then you can use this formula. You can either find your mass flow rate, mass of water vapor using this formula, or you can also determine it by using this formula here, which is shown at the bottom. So that is the skeleton solution for example that we discussed earlier. Now let's look at our next example. So this is an example involving dry bulb and wet bulb temperature. So this is a problem based on 6.4. So you have atmospheric air at 30 degrees C, and the total pressure given to you is 100 kilopascal. Dew point temperature given to you as 20 degrees C. So you are asked to determine these three parameters. So the first one is the relative humidity. Second one is the humidity ratio, or also known as specific humidity. And the third one is the enthalpy of mixture per mass of dry air. Now let's look at the solution. So in order to find the relative humidity, all you need to do is you use this formula, right, for the relative humidity. For that we have to find these two parameters, right, pressure PV and PG. PG is nothing but your P saturation at 30 degrees C, which you can find from the table easily, right? And this is for dew point or 20 degrees C, right? So you can find the P saturation at 20 degrees C, and this is easily found from the table here, right? So P saturation at 30 degrees C, P saturation at 20 degrees C, you can refer to table A4. That will give you the values of this easily, and you will be able to find what is the relative humidity, right? Next, to find the specific humidity. To find specific humidity, you will need to use this formula. So we know what is the total pressure. Our total pressure is 100 kPa. We've already found our PV, all right? So substitute the values here, and that will give you the humidity ratio. All right, so that is done for part B. And then for part C, you are required to find the enthalpy. Again, enthalpy, we will use this formula. All right, so you can find Cp. Cp is again same as what we've discussed, 1.005. You have the temperature given to you, all right, and then use the temperature again in degrees C. Substitute it into this equation because omega is also known. So once you substitute it, you should be able to get what is the value for your H. So that is how you solve problem 6.4. Make sure you do it on your own. I've provided you with a skeleton. You should be able to solve it on your own. Now this is problem 6.5, right? So this problem 6.5 is based on a room which contains air at 20 degrees C and total pressure of 98 kilopascal and a relative humidity of 85% is given. So you are asked to calculate the partial pressure of dry air, the specific humidity of the air, and the enthalpy per unit mass of dry air. So let's look at the skeleton again. So you are given the total pressure, so we can use this formula. We want to find the partial pressure of dry air. So in order to find that, we need to know what is the partial pressure of water vapor. So we find what is our saturation pressure at 20 degrees C, all right? We substitute it into this equation because we know the relative humidity. Point to note here, this is given in percentage, 85%. But when you substitute here, you must convert this percentage to 0.85. So you will have 0.85 multiply with the whatever value that you find from here. That will give you your PV. So substitute PV here. Total pressure is given as 98 kilopascal, and you should be able to find what is your partial pressure of dry air. That's easy. Then to find specific humidity, again we have both these parameters. Substitute it into this equation of your specific humidity, and you will be able to find your specific humidity. And bear in mind, this is the unit, kilogram H2O over kilogram dry air. And similarly, you can also find the enthalpy per unit mass of dry air by using this formula. So give it a try, see what you get for the enthalpy, and please practice this because it will be important for your assignments and exams later on as well. Okay, so with that, this is the end of part 2A, focusing on air conditioning. You are now familiar with all the important equations that you can use to calculate out properties for atmospheric air. In our next part, which is part 2B, we will be focusing on same chapter 4 but on psychrometric charm. All right, thank you.